So this is what you've been waiting for. How do you find derivatives without doing all those darn definition of the derivatives? So before I start doing some examples, I thought I'd talk about the notation a little bit. On this side here, Isaac Newton, you should go read Calculus Wars. That's another book you should read this summer. It's a great story. It talks about Leibniz, this is Leibniz notation. Is he Swiss, German? No, I don't remember. And then there's Isaac Newton, and this was Sir Isaac Newton's notation. They developed it more or less the same time, and the short story for the war is Leibniz published. Newton worked earlier at the work developing calculus, but Leibniz published first, and then Newton got irate and said, "Wow, this is a product of me, of my brain, not yours. I came up with it first." And it was quite a bitter argument for the academics back then. But anyways, I digress. So this means first derivative. That's what we've been doing when we do that limit expression. This means second derivative, which is the derivative of the derivative. And then this is the third derivative. And you can keep going. You could do as many derivatives if you wanted to. But, I mean, usually, mostly all we're going to look at here is up no longer than the third derivative, because that has the most application. We'll get into this later on in this course, but this is the rate of change for if you want to think about position versus speed. So if the first function if the f of x is the position, this would be the velocity. This would be the acceleration. So how much your velocity is changing, and this is how fast the acceleration is changing. And the best physical model I've ever heard about the third derivative is when you're driving down the road, and if you were to be accelerating, stepping on it, and then all of a sudden you see a police officer sitting on the interstate, and you see a police officer with radar on you, you hit the brake and you slow down. That reaction you feel when you slow down is the jerk. I wonder if there's a relation between that, but not, because this was developed long before there were radar guns. But I digress. So, and then again, this is the first derivative, second derivative, third derivative. I honestly use this more. It depends. It depends what I'm doing. But I do like Leibniz notation. I use that a lot. You'll see me using that a lot as we get further into this. One thing that I don't have here that I do want to talk about is these are all nouns. You're talking about this is the first derivative. This is the second derivative. When you see this notation, d dx of f of x, this means take the derivative. Okay, usually there's no slick notation for slick notation like this for the Newtonian notation. It's really a Leibniz notation. Okay, so just don't get confused what that means. So, what about a constant function? Easiest derivative to get. We know the y equals x, or y equals 3. Looks like this. We know the derivative is the slope of a horizontal line is 0. We know the derivative is just another name for the slope. It's the formula to get us the slope of a function. So if the slope of this line is 0, the derivative of a constant is 0. So whenever we have that, that's what you can do. So if you just see if it's a constant function, the derivative is 0. You don't have to do anything more with it. Now, something I found interesting about this book and what they do is that they throw these exponential functions right at you in a hurry. So, and it's great because that way you learn about them and you learn how to deal with them, and they're very, very fun functions to take derivatives of. But what I want you to not do is don't get confused. When do I use the power rule, and when do I treat a function like an exponential function? So think power rule for power functions. Power functions are functions where there's a variable as the base, and you have a number for the exponent. Okay, so if that's the situation, you've got a power function, you can use the power rule. X squared, x to the fifth, x to the 1/2. I mean, those are all variable to a power, so we can apply the power rule. What is the power rule? Well, maybe you've seen this before. Maybe you've watched Nancy Pie or some other video. It's generally what we say is if we have x to the a power, the power rule, if I want to find the derivative of that, look at that fancy notation, huh? What you do is you bring a down in front, so you bring the exponent down in front, write the variable, and then you subtract 1 from the power. Okay, and it's that easy. It beats the heck out of doing the limit as h approaches 0, blah, 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 right? So all those times when you had to find the derivative of x squared plus 3x minus 1, and you had to substitute in that formula with x plus h, we could have just had you doing, okay, these are power functions. In fact, this is a polynomial. A polynomial is the sum of a bunch of monomials, right? So what we can do is we can treat this, I'm going to take the derivative of this plus the derivative of this minus the derivative of that. So 2x, remember, I brought down the 2 down in front. I brought the 2 down in front. And then I'm going to think 2 minus 1. Well, 2 minus 1 is 1. So I could write that as 2x to the first, or just leave it as 2x. The next one's kind of interesting. I have, here, let's see. I'm going to have to leave that exponential functions there. If I have the derivative of 3x, well, isn't that 3 times x? So let's think about this. If I have a number in front of a variable, how do I deal with that? Well, for now, I'm going to just let you trust me on this. When we do the product rule, I'm going to come along. What you're going to do is you see that x has an exponent of 1. We're going to bring that 1 down in front, multiply by what's there, and then take away 1. Well, 1 minus 1 is 0, so isn't 1 times 3 is 3, times x to the 0, and we know another name for x to the 0 is just 1, right? Anything to the 0 power is 1, so that's 3 times 1. So the easy thing is just 3. Now, let's think about what we know. This is a linear, this piece of this function is a linear piece. What's the slope of a linear function? The number in front of the x. So in this case, the slope of that piece is just 3. And then we got a constant. What's the derivative of a constant? 0. So that becomes. So the derivative of x squared plus 3x minus 1 is this linear function. So notice a quadratic function has the derivative that's a linear function. What do you think the derivative of a cubic function is? I hope you think quadratic function. That's right. Okay, so we'll get some practice with this. I don't know if I need to do any more for you right here. Now, power functions are great. Power rule is great. It's easy. Don't forget to take away 1. 2 mistakes that I am famous for making, and I always kick myself when I make them. I'll warn you right up front here that these are the mistakes that I always do, and you're going to catch me on them. What I'll do is if I'll have something like 3x to the 4th, I'll write 12x, and then I'll forget to do anything with the exponent. Remember, take away 1 from that exponent and write 3. I don't always do that, but I have caught myself doing it more times than I like to admit. Okay, so there's that one. Now, what about if I've got an exponential function? What do I do with that? Here, let me do some deleting here. You must admit, this is a heck of a lot easier than doing that limit expression. Okay, can I erase this? Yes, I can. So an exponential function is always in the form of some constant, some number raised to a power that's a variable. So the most common one that you'll see, and that you'll see this week's work, is e to the x. Well, the derivative, remember, e is that number 2.71 blah 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 blah. Okay. There's a great video. Maybe what I'll do right now is let's you can fast forward through this if you want, but let's apply the let's apply the let's apply that limit. Am I going to get myself in trouble if I do this with you? Let me see. I just made a decision. I'm going to go find the video where the guy talks you through it. It's Ed Berger. I don't know if you ever watched an Ed Berger video. But it just so happens that the derivative, he does a great job with it. I don't want to try to steal his thunder. I would just be doing what he does anyway. So I'll link to that in this week's work. The derivative of an exponential function is itself. So if you have e to the x, the derivative of it is e to the x. It's a wonderful thing. So easy. Now, that's not true for all exponential functions, but it's true for e to the x. The other exponential functions have a special piece, and we'll find Ed Berger's video. So if I have e2 e to the x, the derivative of that is going to be 2e to the x. Remember, those constants just come along for the ride. Same here. So it's pretty easy, and I've got an example right down below here that's from your homework that you'll have to do. Let me stop this video for a minute. All right, so here let's get some work done now. Let's do one of your exercises. I'm going to do a couple of things here. One thing I'm going to do is, you see how it's written as 7x to the 4th over 4? We can write this as 7 over 4 times x to the 4th. That way it looks like I get this constant in front of a power function, and that makes it pretty easy. And remember, I can break these functions up into pieces. So this piece is a power function. I'm going to just bring the 4 down in front, multiply by what's there, and take away 1. So 7 divided by 4 times 4 over 1, those 4's cancel out, thank goodness. I'm left with 7. 4 minus 1 is 3. So that's the derivative of the first piece. Then we have that negative 3x. Well, I'm hoping you can tell me that the derivative of that is negative 3, right? And then I've got this e to the x function. Notice here's a number in front of it. So I just showed you, or I told you, I didn't show you why, I just told you that the derivative of that 8e to the x will just be itself, 8e to the x. And we're done. And that's the first derivative. Now, if I want to do the second derivative, I'm going to do it again. So see, I didn't do that whole problem here. See how it's saying first derivative and then second derivative. So part 2 of this question would be find the second derivative. So the same thing. I'm going to bring 3 down in front. So 3 times 7x to the second, right, which would be 21x to the second. The derivative of a constant's 0, so that piece is gone. If you want, you can write plus 0 or minus 0. And the derivative of 8e to the x is 8e to the x. And so what we'd write for the second derivative would be 21x squared plus 8e to the x. So that's d2y dx2, since they're using Leibniz notation. Okay? So hopefully that makes that pretty easy. Okay, the next shortcut rule that we need to learn is the product rule. What the product rule is when you're multiplying two functions. And here it is kind of generically, and all the textbooks talk about this. And we're going to look at, not going to do it in this video, but one of your homework exercises has functions defined in terms of u and v, and I'll do a video for that later. So this is what the product rule says. And different books teach this different ways. I'm going to show you the way I learned it and the way I usually teach it, okay? And you can do it backwards. It doesn't matter because it's an addition. So, but what you do is you do the first function times the derivative of the second plus the second function times the derivative of the first. It's that easy. Some textbooks, and I honestly don't know how this Taylor textbook, I haven't looked at this section. They'll write this way with VU prime plus uv prime. See, it's the same thing. It's addition. It doesn't matter. Addition is commutative, so it doesn't matter what you do. What you like, if you like doing it this way better, go for it. If you like doing it this way better, go for it. Same work. So here's a function. It's got a power function, an exponential function. So yeah, using the power rule, well, I mean the product rule, I see as a product in between them, a multiplication between them. So I'm going to take the first function times the derivative of the second, and fortunately the derivative of e to the x is e to the x, plus the second function times the derivative of the first, and that's x squared, so we bring the 2 down in front, take away 1 from the 2, so 2x to the first, and we're done. And that doesn't clean up very well. We could do some factoring. You could factor out an e to the x if you wanted to. You could factor out we could factor out an x e to the x even, but we don't need to. So that's the derivative, and that is the derivative of that product. Okay, so the quotient rule is our next shortcut rule that we need to learn. And what the quotient rule is, if your function is defined by the ratio of two functions, in other words, you get a rational function, what you can do is you do the derivative, the bottom times the derivative of the top minus the top times the derivative of the bottom, or the bottom function squared. And then you try to clean it up as much as you can. My least favorite rule of all of them that we're going to do in this course, and one way that I keep it straight, and I don't want to prejudice you, probably like the quotient rule. It works well, but I find it kind of cumbersome. The reason I find it cumbersome is that extra negative sign. So if you think quotient rule bad, the negative's there. Product rule good, there's a positive there. Okay, that's one way that I keep it straight in my mind. I don't want, like I said though, I don't want to prejudice you against the quotient rule, but that's just one of my quirks. Okay, negatives forever. I'm forever dropping a negative sign and getting something wrong because of that. So here's a quotient. I got to find the derivative. So the bottom function is 7x plus 5. Now I do the derivative of the numerator. Well, the derivative of the numerator, 9x minus 2, is just 9, right? That's the slope of that linear function, so it's just 9. Or treat it as two separate power functions, right? And use the power rule. So 9 minus the top, 9x minus 2, times the derivative of the bottom, which is just 7, all over the bottom squared. And of course, they're making us clean it up. They will. My suggestion is don't clean up the bottom. Leave it as the factor squared. The top, we have to combine like terms, remove parentheses, find like terms, and combine like terms. So what is that? It's going to be 63x plus 45. If I distribute that 9, right? And then I'm going to distribute a negative 7 through each of these. So minus 63x plus 14, and then let's get our like terms together. Oh, that's nice that seriously. That's gone, I'm liking this problem. So 45 plus 14 is what? 59 over 7x plus 5 squared. And I squared. So I'll be very surprised if MATLAB will make clean that FOIL at the bottom. Usually I don't have to. Because you want to know when that equal to 0, right? So it's easier to leave it factored. So that's the quotient rule. Kind of painless here. It's not too bad, but just watch. See, do you see that negative, missing that negative? And I've seen some of you do this. You miss that negative, so just be careful. So this is one of your homework problems in section 3. And notice it's written as a product, but that negative exponent, right? Negative exponents mean you take the reciprocal. So what we really have here is a rational function. So for now, you want to take that, rewrite it as a rational function. Now, because it's a quotient, apply the quotient rule, which remember is if you want to stop this video and try it, you can, or I'm just going to show it right now. So the denominator, the bottom, times the derivative of the numerator, which is 6, minus the numerator times the derivative of the denominator, all over the denominator squared. And now we do the cleanup. Let's see, we're going to distribute that through, so what's that become? 18t minus 12, and then minus 18t plus 3. They're kind of setting us up by always having the 18, the t's in the numerator cancel out. That doesn't usually happen. Just warning you. Sometimes some of them will cancel out, but not as nicely as this. So what is that? Negative 9 over 3t minus 2 squared. At least they're taking it easy on you when you're first learning this stuff. So that's that derivative. Okay, the other thing that happens is they love to throw radicals at people and at us. So what they set you up to use the power rule here. And notice there's an exponential function there too. But sometimes what they'll do is they'll do this to you. This is a radical, right? Plus 3e to the 5th. And what's the derivative of a radical function? What a pain. So what we do is we rewrite them as an exponential. Remember, it's t to the 4th divided by 3. Remember, the index is the denominator. And this is good because what I usually do is when I'm working with radical functions, and I know this is a radical function, is I'll treat it like a power rule. Rewrite it so it's a rational exponent. Do the power rule, and then I'll take that answer and rewrite it back in a radical form. For this problem, they aren't asking you to do that, and I wouldn't do that since they gave it to you as a radical already. But to me, it's easier to work with a radical than it is the rational exponent. But we'll get there. We'll cross that bridge when we get there. So, power rule, right? So, I'm going to bring the 4/3 down, times it by the 3t, and then remember how we subtract 1? Well, 4/3 minus 1, those are fractions, right? So 4/3 minus 3/3, 3/3 another form of 1, that's to the 1/3. And I guess that's all we got to do there. Plus, remember, then that's 3e to the 5th. This is a good question. I didn't notice that. What's e? Is e to the 5th a function, or is e to the 5th a constant? It's a constant, isn't it? It's 2.71 whatever to the 5th power. So that's a constant. So what's the derivative of the constant? 0. I didn't notice that when I did that. I was thinking it was going to be would have e to the x left. Oh, that's interesting. I like it. I like being surprised. I like being surprised and getting them right. I don't like being surprised and getting it wrong. Here, that's the 3's cancel out, right, because of fraction. So 4t to the 1/3. Now, Dan LeMay to get this question right, I would enter that in. But what I would do later on when we had to deal with it, I would rewrite this way to be able to work with it. But that's aside the point. Very, very good. I'm glad I grabbed this question.